Hello, everyone. Welcome to my presentation. My name is Chia-Cheng. I'm the presenter of our work entitled Deep Reinforcement Learning Based Platooning Control for Travel Delay and Field Optimization. And this is a joint work among Department of Computer Science, Institute of Transportation Studies, and Department of Statistics, and Department of Civil and Environmental Engineering at UC Davis. And this is my outline for today's presentation. Today I will be talking about our motivation and the problem we want to solve and the method we propose, and we will elaborate our experimental result and conclude this work and talk about a little bit about our future work. Okay. So I believe people living in urban cities suffer at least once in their lives from traffic congestions, um, especially for those who need to commute. This scene should be the daily scene they will face. And high population usually result in bad traffic based on the INRIX report at the right-hand side. Congestions happens very often in highly dense cities during peak hours. In other words, people spend more time on driving with a very slow speed, and this will reflect on their driving cost. For example, the congestion cost for each driver was close to 1,400 US dollar and 100 hours in 2019. This leads to higher emissions and cost in fuel consumption, particularly at this moment when the gas cost is extremely high. This is not a situation people would like to see. And in emissions, the breakdown by different areas is shown here. And transportation alone contributed more than 1/4 of emissions in 2020. Among the transportation at the right-hand side, the light and the medium vehicles were 57% and 26% respectively. Based on this fact, a great amount of fuel consumption, emission, and cost can be reduced if we can optimize fuel usage in transportation. So the motivation being set in this work is to find out a platooning control model that can learn from a given environment with as less human intervention as possible to optimize the fuel consumption and delay. Um, but how the platooning control can help the optimization of fuel consumption and delay? In our previous simulations, we found that traditional method can achieve up to 40% of reduction in the delay and emissions. With that being said, it is too complex and time-consuming to complete the entire computation. Therefore, this is where a machine learning-based method can come in, as well as consider connected autonomous vehicles technologies. And connected autonomous vehicles have been quite promising technologies as new wireless technologies are rising. So we propose a deep reinforcement learning-based patterning control with connected autonomous vehicles technologies to apply appropriate manipulations such as acceleration, deceleration, or whether or not split a platoon. And the experiments were conducted on a corridor where four consecutive intersections are signalized, and traffic movements with a fixed route, for example, from west to east, from north to south, are controlled by traffic lights with fixed time signals. And we assume a high penetration ratio of connected autonomous vehicles. And information such as velocity, acceleration, deceleration, and the headway can be shared with extremely low latency by 5G wireless uh, technologies. And platoons with close following vehicles arrive periodically, and their platoon maneuvers are controlled by a deep reinforcement learning-based platooning controller. Okay, and our proposed solution to this problem is deep reinforcement learning method, which is an unsupervised learning framework, and we use a deep neural network as a functional approximator to approach the optimal Q values. The deep reinforcement learning agents will learn from the given corridor. For each time slot, a state and the reward were observed from the environment. Then the agent will determine which action needs to be taken in order to maximize the expected cumulative reward. Right. So first, our state, right? We formulate arrival timing vector ATV as our state, and it is formulated as a vector of arrival timings that will be assigned to vehicles in an individual platoon. And an arrival timing for each vehicle is determined by the three variables proposed in the following work. They are cruising time to arrival, earliest time to arrival, and latest time to arrival. And they are defined by the following formulas. And feel free to check this paper if you are very interested in the definition. But the main idea of applying these variables is to calculate the optimal arrival timings and assign them to vehicles in a platoon and see if a platoon needs to be split, accelerated, or decelerated. Okay, and here I'm going to show you a concrete example. First, we have a set capitalized T here that includes all green intervals. For example, from 1 to 30, from 51 to 80. The capitalized T includes all green intervals here. And the following rules indicate how to determine the optimal arrival timings for vehicles. So these rules also came from the same work here. Feel free to check if you are interested in it. So here is the example. If say there's a platoon of 6 vehicles approaching to an intersection, and after their optimal arrival timings are calculated, we found that only the former 3 vehicles can pass the intersection without changing anything, which means they don't need to burn more fuel to accelerate it, and they are having very smooth trajectories. But for the later 3 vehicles, their earliest and cruising time to arrivals are in the red interval, and only their latest time to arrivals appear in the next green interval. So in this case, latest time to arrivals will be assigned to the later 3 vehicles as their optimal arrival timings based on the rule given here. So by doing so, the later 3 vehicles will first decelerate and then accelerate to avoid fully stop. And arrival timing vector of platoon has information of different arrival timings for vehicles. And this information helps the deep reinforcement learning agent to recognize some patterns when platoons need to be split to avoid fully stops and unnecessary accelerations or deceleration. And because of fully stops and unnecessary acceleration, deceleration, or platooning manipulations, which will lead to extra delay and fuel usage. So the number of these misbehaviors has to be minimized to achieve optimal delay and fuel consumption. Okay, and based on arrival timing vectors or state of individual platoons, the actions that were assigned can be different. And the main goal is to optimize fuel and delay by reducing unnecessary stops, acceleration, deceleration. So the actions considered in this paper are 4: split, acceleration, deceleration, and no operation. So for a case when only a part of members in a sample platoon can pass an intersection at the current green interval, then split need to be taken. For another case, when all the members in a sample platoon can pass an intersection, then acceleration um, has to be applied. On the other hand, if not all the members in a sample platoon can pass an intersection, then they have to decelerate first. Moreover, we have an um, action called no operation here because speed or split won't be frequently um, changed. For example, once the optimal action was applied, there is no need to alter the speed or size again and again because the platoon can keep the same speed and size and then pass an intersection. Okay, so recall that our goal is to minimize the number of stops and unnecessary acceleration, deceleration to reduce delay and fuel consumption. So the number of moving vehicles is considered as the reward in this work. The vehicles with any speed equal to or um, larger than the equal speed. For example, 15 meters per second or 34 miles per hour are considered as the moving vehicles. And last but not least, and policy learning is used to learn the optimal actions based on the given reward from the environment and a previous state action pair. So why these are here is TD target calculated by the reward and the Q value of the next state and action. And the TD target is used to get loss and by differentiating the equation here and the agent can get a partial derivative and will know how to fine-tune the neural parameters to get to the optimal action that will return high rewards. Okay, and next I will show you the result after training. So the agent was trained by 700 episodes. In the first episodes, pre-training was performed. That is to say, in this stage, the agent randomly select actions rather than selecting some optimal actions. This is mainly for exploring some potential actions that would return higher rewards. Okay, and the figure at the left-hand side is the reward and the average delay, and the figure at the right-hand side shows the reward and the average fuel consumption. And after the pre-training stage, as it had learned from more and more episodes, the reward started to um, get higher, and the average delay as well as fuel consumption got lower. And these figures show that after training, the agent is able to pick up the knowledge from arrival timing vector and learn how to either split platoons or control the cruiser speeds of the platoons to reduce fuel usage or delay by vehicles. Okay, so to conclude our work, this work demonstrates that the feasibility of applying deep reinforcement learning to reduce the delay and fuel consumption compared to traditional methodology. And in our future work, we want to consider multi-models traffic and also consider um, complex scenarios like large network um, in our future work. Thank you very much for your attention, and this is all for my presentation today. Thank you.